Myself. Good morning, I'm Victor. I'm at QPSI. I'm a security engineer at QPSI. And it's an honor for me to introduce the next speakers for today. These are two very bright individuals from Austria. We have Barbara Gigerl and Claudio Canella. Barbara is a master's student at TU Graz. She just submitted her thesis on the topic of computer security, and will now move on to submitting her second thesis in the field of data science. Claudio is a PhD student in the Corsair group, so these are the guys who did Meltdown and Spectre. Claudio actually was also in the news this week as one of the authors of this Store to Leak paper. And he's currently interning at hARM. His research focuses on microarchitectural attacks, side channels, and system security. And I hope we're almost set up because I'm running out of text.
Give me a second.
So I can give you maybe a preview of the talk. So I think this will be about speculative execution, out-of-order execution maybe, and whether or not this applies to Qualcomm and hARM, and what will happen in the future perhaps. So please welcome the next speakers.
Okay. Welcome to our presentation about transient execution attacks. This is like a follow-up presentation to the one our colleagues gave last year. And we will investigate if those kind of attacks are still harmful. So I'm Barbara. I'm a master's student at TU Graz.
Yeah, so like Victor said, I'm a PhD student. You can always reach out to me on Twitter or send me an email if you have any questions. So, or just talk with us. We're still here till Sunday.
Okay, so let's start. You all may remember when Meltdown and Spectre were discovered. It was all in the news. So, for example, in Fox News, also CNN had it in their news shows, and even BBC did some report about it. So, what we can get from that this is serious. But what is what is the basis of this? The basis are side channel attacks. If you have a piece of software and you can say or guarantee that this software is bug-free, it does not mean that execution is safe, because information may leak because of the hardware, which is kind of underlying the software. And this leakage can be exploited through side effects, which we get from things like power consumption or the execution time of the program, and even CPU caches. CPU caches are microarchitectural components, and in general we have the instruction set architecture, which defines like an abstract model, which is implemented by a CPU, like the x86 or ARMv8. And this serves as kind of the interface between hardware and software. And the microarchitecture itself is the practical implementation of this instruction set architecture with all the components. For example, Intel CPUs and AMD CPUs implement the x86 instruction set architecture. So microarchitectural components are part of this microarchitecture, and modern CPUs contain multiple of these elements. For example, caches like data cache or an instruction cache, buffers, for example, a load buffer, and also predictors are part of these components. And the good thing about that is that the programmer, so the guy who writes the software, does not have to care about that. So they are transparent to him. And there are timing optimizations done by the CPU. And the negative part is that we get side channel leakage from that. So for now, let's focus on the CPU cache, and let's look at some example. We have a program consisting of 2 printf statements. In the middle, we see a CPU cache, and on the side, we see the DRAM. And when the first printf statement is executed, we have to get the value of I, and we see if I is contained in the cache. It is not, so a cache miss happens. We send a request to DRAM, get a response, and I is finally present in the cache. So the next printf statement happens, and we again have a look at the cache and see I is there. So a cache hit happens. And the first printf statement was very slow because we had the load from DRAM, and the second was much faster because I was already in the cache. And when we look at how fast this really is, we can see that there is a big difference in timing between accessing a cached variable and accessing an uncached variable.
Yeah, and with this timing difference, we can do something like what we call a flush and reload attack. We have an attacker, we have a victim, and they share some memory like a common library. And the idea then is if it's shared memory, then it is present in the same cache line in both the attacker and the victim. So in this attack, our attacker can then just flush the shared memory from the cache, yield the CPU to the victim, who performs some access. While doing so, the victim loads data into the memory or into the cache, which is then accessed again by our attacker, and he can learn what the victim was doing. But we can take this even one step further, because based on this timing difference, we can now do something like a simple toy example here. We have just some memory, and I'm a bad programmer, so I access a null pointer, and that should kill my program. And should not execute the then following instruction, where we just access some page in this array. But what actually happens is that if we then do a flush and reload attack over all the pages of the array, we see a cache hit exactly at the index. So the unreachable code line was actually executed. And the exception was only thrown afterwards. So the out-of-order instructions have already left a microarchitectural trace. And we call those instructions that are executed but should not have been executed transient instructions. But we can also take this another step further by adding another layer of indirection. Instead of accessing some fixed value, we first read kernel data, for instance. And if you access kernel data from user space, you're getting a page fault. And now we access based on this, on the data that we read, encode it in the cache, and check whether any part of it is cached. And as we see with Meltdown, this actually happens. So the index of our cache hit reveals what the data was. So the permission check is in some cases performed too late. And this is called Meltdown. So the CPU uses the data in the out-of-order execution before doing the permission check. And this allows Meltdown to read any kernel address, and as the physical memory is usually mapped in the kernel, you can read arbitrary memory. Previously, it was believed that you can only read data from the L1, so Intel was very clear in the first statements on this. And we were able to show that you can also leak data from the L3 cache or from memory, but it is slower. And you can also leak data from uncacheable memory regions. If you have one hyperthread that constantly accesses the data legally, then you can leak it from the line fill buffer, which is one of the papers this week showed. So how can we fix this? Well, the kernel addresses in user space are a problem. So why don't we take the kernel addresses and remove them if we don't need them? So we have to do this because the user accessible check in hardware is not reliable. This is how address space isolation basically looked like before. So we have the user space with the kernel space, with the barrier between, and the kernel space was able to see everything in the user space. And with Kaiser, which was one of the patches that we proposed for another paper, the kernel now still has the view of everything, but the user doesn't now, the kernel is no longer mapped in the user space. So if it's not there, you cannot leak it. Linux implemented this as the kernel page table isolation. Apple also released some updates, and Windows calls it kernel virtual address shadow. Does it now mean that our problem is solved? Well, Meltdown is fully mitigated in software, and the problem seemed to be solved, and that there's no attack surface left. At least that was what everyone thought. But there are no bugs, there are just happy little accidents. So basically, Meltdown is a whole category of vulnerabilities. And it's not just the user accessible check that causes a problem. And we can take a closer look at how all those checks work. So we have paging in our computers. So we use virtual address spaces to isolate processes. And with those, the physical memory is organized in so-called page frames, and we map those page frames using page tables to physical memory. On x86, it's basically like that. We won't go into too much detail here, and just look at one of the entries in the lowest table. So this is how a page table entry on x86 looks like. We have the physical page number, we have some ignored bits, and then some access permission checks, like in this case the user supervisor bit, which tells you which privilege level that you can access the data.
Okay, but as we already heard before, the user supervisor bit is not the only bit we can use for an attack. There's another bit, the present bit, which indicates if the page is mapped or not. And this we can use to build an attack called foreshadow. Foreshadow NG, or level 1 terminal fault, as it is also called, is exploitable from virtual machines. And it allows leaking data from the level 1 cache. And the mechanism is exactly the same as it is in Meltdown. It's only a different bit. So instead of the user supervisor bit, we use the present bit. Okay, now let's look at some example. On the left side, we see a page table, which has some page table entries. And we want to do an address translation from the virtual address from inside a VM to the host physical address to see our level 1 cache here. So if the page table entry is present, we get our host physical address. In parallel, the level 1 cache lookup happens with this physical address. And yeah, we get our data. But what happens in the case when the page is not present? The thing is, the address translation will fail, but the level 1 cache lookup will still happen in parallel to that. And which address is used for that? The one which is in the page table entry, which is in fact attacker controlled. And by this, we can leak, in fact, the whole level 1 cache. Okay, and how can we now fix this? So Kaiser and KPDI does not help because it's another bit. There are only software workarounds. For example, flushing the level 1 cache when we enter the virtual machine, or disable hyperthreading. But these workarounds might not be complete.
So I already mentioned that with Meltdown as well as with Foreshadow, we always get a page fault. So the natural thing then is, okay, what else does cause a page fault? So we have Meltdown US, which is basically introduces the new names that we propose instead of like Spectre variant 3 point something. We call it Meltdown, and the bit that is actually exploited here. So Meltdown US is the user supervisor. We leak it from L1, L3, and the LFB. Meltdown P, as it is the present bit. But we also have Meltdown RW, which just exploits the read-write permission check on a page, and Meltdown PK. So this is a feature that Intel introduced with so-called protection keys. Thankfully, ARM is not affected. Only Intel has full vulnerability support, and please don't quote me on this. So we also tried some others, like Meltdown with the executable bit, or Meltdown SM, which is basically SMAP, or privilege access never. And now we have seen a few versions. What is the root cause here behind Meltdown? We have some operation, and it tries to access some data. And based on, there's a data dependency to the next instruction in the pipeline. but we access like kernel memory. So we get an exception as we're not allowed to do it. If we don't have meltdown if we just throw away the result of this access and forward some kind of dummy value to the next instruction. But with meltdown, we actually forward the data that was illegally read, that should never have happened, and pass it on to the subsequent instructions, which allows us to leak the information. And the exception then is only raised at the retirement phase, but at this point it is too late. So we've seen page faults, but there's also a few other things. So for meltdown, we classify everything as a meltdown attack that exploits a fault. So as soon as you have a fault, you're in the category of meltdown. And there are many different things. So you have meltdown PF, which I already discussed. You have meltdown NM, which is a device is not available. This was previously called lazy FP. Meltdown AC with alignment checks, division by zero, stack segmentation. Meltdown BR is also so not only Intel, there is also the first AMD version of Meltdown, and Meltdown GB general protection fault. So is Meltdown a fully solved issue? No, we've seen it this week. There were new discoveries in this direction. So the tree is easily extensible, like we have done in the new papers, and we learned that silicon fixes might not be complete.
Okay, so we call this class of attacks transient execution attacks, and meltdown is not the only one. There's a second class called Spectre, and Spectre exploits, instead of faults, speculative execution, so kind of the prediction of data and control flow. In speculative execution, the CPU tries to predict which instruction to execute next, and for that, it uses a thing called a branch predictor, which gives recommendation on that. And the branch predictor learns from events in the past and gives prediction based on these events. And if this prediction was correct, we're happy because execution was really fast. We could do more things in parallel. But if it was not correct, we have to discard the results and do a rollback. Okay, so but now let's see how we can exploit this by an example of a Spectre BHD attack. As we've already mentioned, we introduced a new naming scheme, which we hope is less confusing. We, instead of calling Spectre variants by numbers, we always have this Spectre dash and the microarchitectural element they use. In this case, it's the pattern history table. Okay, in our example, we have memory on the right side and some kind of shared memory on the left side, and a simple program, which checks if index is less than 4. If index is 0, the pattern history table, our predictor, does not kind of know anything and just recommends to speculatively take the else branch. However, the CPU is wrong, and we have to execute the then branch. And then we encode D in our cache. So if index is now 1, the next iteration, if, for example, this is executed in a loop, the pattern history table or the predictor says, okay, take the then branch, because this was taking the time before when we looked at the branch. And the CPU is correct, speculatively executes this, A is encoded in the cache, and we're fine and happy. The same thing happens if index is 2 and if index is 3. Okay, but now let's look at the case where index is 4. So the condition will actually evaluate to false. The predictor again tells us to take the then branch because it has seen that the times before, 4 times before. And we will speculatively execute the then branch and encode K in the cache. But the CPU was wrong, and we should have actually taken the else branch. The architectural operations are rolled back, but K is still in the cache, and this is kind of the cause of Spectre. Now let's look at that in a more general setting. We have an operation, we have a prediction, and following that prediction, we have a second operation which is done. So everything which happens before the prediction is possibly architectural executed, and everything after that is transiently executed. Now this operation retires, and also prediction retires, which means we know the result. And if the prediction was wrong, we have to flush our pipeline and kind of tidy up everything, but we forget about the caches. Okay. So in CPUs, we do not only have the pattern history table, but we have many other predictors. For example, the branch target buffer, the return stack buffer, or we have also some predictions which say if a load matches a previous store. And and some of that are even shared among processes. So if you have simultaneous multithreading, these microarchitectural elements are shared. And one essential part of Spectre attacks is mistraining. So an attacker who wants to exploit that has to kind of train the predictor to do a wrong prediction. And we have 4 different ways to do that. If the attacker is in the same address space as the victim, he can just take the virtual address of the branch and take the branch a few times. Why the virtual address? Because the predictor uses a subset of the bits of the virtual address to address the things in the buffer. Okay, and the attacker can also be in the same address space as the victim, but use a congruent branch. So a branch with a virtual address which matches the same as the actual branch he wants to exploit. And since predictors are shared, the attacker can also be in another address space as the victim. If he knows the virtual address of the Spectre gadget, he can use that, or he can also use, again, a congruent address. Okay, and what I did in my master thesis was to analyze things about speculation windows. As an attacker, you want to have a speculation window which is as large as possible. And so I had 2 questions. How large are speculation windows if you use different gadgets, and what is the gadget which kind of maximizes your window? And I did this on multiple architectures. I will only show you the results for ARM. And I used the Spectre BHD attack with flush and reload. And in one run of the experiment, I tried to leak 1 byte with such an attack. And in one test, I did n runs in m different processes. So in total, n times m bytes which I tried to leak. Why different processes? Because we saw effects caused by ASLR, which had some impact on the success rate of the attack. Okay, and how can we actually enlarge this speculation window? We can use slow operations in the condition or in the Spectre gadget, because if the operation is slow, the evaluation of the condition takes longer, and we can have more time to speculatively execute things. Or we can use a fast operation and make it slow. Slow operations would be dependency chains, accessing variables without the entry in the cache, accessing variables without the valid TLB entry, and vector instructions. And how can we make fast operations slow? We can use port contention for that. Since our ARM CPU did not have simultaneous multithreading, we could not test port contention, and we also skipped vector instructions. Okay, so in order to find out how often we have to repeat the experiment, so to find values for n and m, we did a preliminary study which shows us how often do we have to repeat the experiment to get stable results. And it turns out if we set m to 10 and n to 100,000, we get stable results. Okay, so now let's look at them. A dependency chain looks like this. You kind of repeat an instruction over and over again, and each instruction can only be executed if the previous instruction finished. In this case, we have multiplications. We set the result, we store it in a variable, and the Spectre gadget actually uses this result. Okay, and this was our yeah, this is what we found out, that the chain length has a huge influence on the success rate of the attack. And the speculation window size we measured with 57 instructions, which was reached at a chain length of 22. So 22 was the shortest chain length, which gave us this speculation window. The same we did with cache misses. We constructed a chain of pointers, flashed these pointers, and accessed them in the gadget. And it turns out this always works out really good. And we reached a maximum window size of 57 already at the length of 1. And the third thing we tested was a TLB miss. We did not do this in a chain, but only with one variable. So we allocate memory, flush the TLB, and access it. And the window size is again 57 instructions, and our success rate is 97%.
So now we've heard that we can mistrain in from different places. We've heard how we can prolong our speculation window, but how does the transient execution attack usually happen? So we have 5 phases. We have first the pre-phase phase where we clear the cache and everything. So we just try to get the microarchitecture in a state where we can then actually do the attack. And also the mistraining happens in this phase. Then we trigger we use the trigger instruction to get into the transient execution. So for Spectre-PhD, that was basically our condition. And then in the third phase, we encode the data in the microarchitecture. This can be whatever we want and whatever can be exploited. In the fourth phase, the CPU then realizes the mistake and reverts all the architectural changes. And in the fifth phase, the attacker just reconstructs the data from whatever microarchitectural element that is used. Now, we looked at all the different transient execution attacks that have been published and tried to classify the different things they use for bringing the microarchitecture, for instance, into the correct state. So for the cache covered channel, you flush, prime, or evict the cache. For Spectre-PhD, you poison the pattern history table. For Spectre-PTB on the branch target buffer or the return stack buffer, you poison those elements. Then you use some trigger instruction. For instance, for Meltdown US, you move data from somewhere you're not supposed to. You then control how you encode the data. So you can use loads, you can use AVX, and just put it somewhere into the cache, for instance. And in the fourth one, we don't have gadgets, so this is something the CPU does. And in the fifth one, we reconstruct by using flush and reload or doing some exception handling and then decode it from the microarchitecture and everything. And so we've heard now that with Spectre, we have the transient cost. It's basically the same that we've seen with Meltdown, but in this case, everything that uses a prediction is Spectre. We have seen then there are different microarchitectural buffers, so pattern history table, branch target buffer, and so on. We've also seen that we can do mistraining in different ways, and those are all the different ways that we actually experimented on. So we have proof of concepts implementation for all of them, and so everything that is in red we were able to show. And then the question comes naturally, how do we fix this? Well, Spectre is not a bug. Spectre is a useful optimization that without it, our CPUs would be much slower. So we cannot simply fix it. I mean, the easy fix would be just disable speculation. So as we cannot do this, we need some workarounds for critical code parts. And we looked at all the published research on defenses and categorized them in 3 categories. So the first one is we can just mitigate or reduce the accuracy of our covert channel. If we add some noise to the cache covert channel, we cannot reconstruct the data. The second one, we can mitigate or abort the speculation when we detect that something is going on. And in the third phase, we can just ensure that the secret data cannot be reached at all. If data is not present, like for instance, for Meltdown we did with Kaiser, then you cannot encode it. And we did then an analysis on all those papers. So in the top, we can see all the published research. We have things that require hardware changes, like InvisiSpec, SafeSpec, DOG. Other things like that have been proposed by ARM, Intel is, for instance, serialization. So after every branch, you can insert a serializing instruction. And we evaluated all of them on ARM, Intel, and AMD. And it turns out that some of them are able to mitigate an attack. For some, we were able to show that it at least partially mitigates them. Some do not work. And for some, there's no proof of concept implementation, or we do not have access to hardware. So we were only able to theoretically argue that it should work. Some should work partially, and for some we can just argue, like for the InvisiSpec, SafeSpec, DOG, they only focus on like the cache covert channel. So I substitute the cache with something else, and I can still leak the data. And some are just not meant to defend against a certain kind of attack.
Okay, so finally I want to clear up some misconceptions people have about Spectre attacks. Many countermeasures only consider the cache to get the data, but the cache is only like the channel you use to transmit. There are other possibilities. For example, we've seen Smother Spectre, which uses port contention to finally transmit the data. Or a NetSpectre introduced an AVX-based side channel. And the thing is, the cache is just the easiest way to do that. And current mitigations are therefore either very cost a lot of performance, or they are incomplete. And we need more research. We need to do more research on both attacks and defenses. Because if we do not understand attacks, we cannot build defenses which are complete and efficient.
Yeah, so here, before we conclude, we can see our whole tree that previously we came up. There will be a new version of this tree as soon as we've updated it with the new results that came out this week. And to conclude our talks, we would just say that transient execution attacks, they are a novel class of attacks, and they are extremely powerful, and we believe that we are only at the beginning. So we should look into more. There are many different optimizations that have not yet been investigated and that might be exploitable. So if anyone wants to join in the fun of doing this research, you can always contact us. So thank you for your attention, and if you have any questions, feel free to ask.